Okay, my phone messed up a minute ago when I was doing the first video, so that's why it's in two parts. But I believe we got to this part where I was explaining what the mean value theorem says. And basically it says, if f is continuous on a closed interval from a to b, and you can take the derivative of it across that interval, then there is some value c where if you take the slope of the secant line that is formed between the endpoints a and b, then you can find some place between a and b that has the same slope. The slope of the tangent line is equal to the slope of the secant line that's formed between the endpoints. So this slope right here is f of b minus f of a, or y2 minus y1 over b minus a, x2 minus x1, where the first point, x1, y1, is a f of a, and the second point, x2, y2, is b f of b. So it's the slope of the secant line formed between the endpoints. So real quick, let's just draw a couple of graphs just so we can get a picture in our head of what's happening. What if I've got some value here a and some value here b? So the deal is, here's a, b can be anywhere. It could be, let's make it up here. Somehow a's got to get to b. We could have a dip down and go up and go down and get to b like that. We could have take a more direct route to b. The a and b do not have to be the same value, although they can be. A has to get to b. What if we just had it loop like this? All right, that's fine. What does the mean value theorem say? It says that if you take the slope of the secant line formed between the endpoints, so let's just draw that secant line on there, right there. It says that there is at least one place where this graph, the tangent line of this graph, will be the same as the slope of the secant line. So a real easy way to do it is if you have a ruler, you just kind of move it until it hits tangent with the graph. There's one place right there I see where it's going to be the same. If I keep going, there's another place I can see where it's going to be the same. And then I can see another place. What if I go up? Till it hits tangent, there's another place. So we can see in this graph that I just drew, there's three places. 1, 2, 3 values of x where it satisfies the mean value theorem. What if I took a more direct route? Okay, what is the slope of the secant line here between a and b? You could just draw that and say, okay, where is my graph going to take on that slope? Well, it's easy to do with this just sort of estimating. You can go down till you see where it's going to hit, and it looks the same. That looks like it does it. And so right here would be your value of c. So that's just to illustrate what the theorem says. So in this first example, number 1, it says the graph of the function g is shown, and it gives us this graph. Now the reason you see orange on my graph is because I made this video already and my phone messed up. So pretend like the orange part's not there. We'll get to that. Part A says verify that g satisfies the hypothesis of the mean value theorem on the interval from 0 to 8. Okay, here is g. It is a continuous function, and you can take the derivative on this interval from 0 to 8. So it satisfies the conditions. Then it says estimate the values of c that satisfy the conclusion of the mean value theorem on 0 to 8. So if this is 0, and this is 1, 2, 3, 4, 5, 6, 7. This is 8. These are the endpoints that we're talking about. So what is the secant line between these 2 points? Let's just see. Let's draw it. There it is. Where does it look like our graph has that same slope? So what you can do, again, if you have a straight edge, it makes it real easy. Say, oh, it looks like maybe it satisfies it right there. And let's see, where else might it satisfy it? Go to your tangent with the graph, and it looks like it's going to satisfy it right there. Let's see. Then it says estimate those values. So if you say, where does it look like this is hitting? this looks like this is hitting maybe at x is equal to 2. And this looks like has the same slope at x is equal to 6. So 2 and 6 are the values that satisfy the mean value theorem for this one. Part C, estimate the values of C that satisfy the conclusion of the mean value theorem on the interval from 2 to 6. So if 2 is the first point and 6 is the second point, then in the orange is what you see where I drew the secant line between there. And so it said, where does it look like it satisfies the value? So I took my ruler and I went up on the curve till I hit there, and it looked like it satisfied it there. And then it looked like there was a little piece of the function that satisfied it here. So I estimated those values and I said, this looks like it's hitting about right here. And I went down there and I said, that looks like it's about 3.5. And then right here, it looked like it was hitting about maybe 5.5. So that's what I saw when I did it between the values of 2 and 6. All right, let's look at the last problem. Verify that the function satisfies the conditions of the mean value theorem on the given interval. Then find all the numbers C that satisfy the conclusion of the mean value theorem. So for part A, here is our function. Let's look at that function. It is a polynomial. Polynomials are continuous for the entire domain, and they are smooth, continuous curves, so they are differentiable all the time. So it does meet the conditions. These are the endpoints. So what it says is that the slope of the secant line that's formed by the endpoints would be f of 2 minus f of negative 2 divided by 2 minus negative 2. So f of 2, if you put that value in, you will find that it equals to 4. F of negative 2, if you evaluate it at negative 2, it's 0. Over 2 plus 2, we get 4 over 4. So the slope of the secant line through the endpoints of this graph on this interval is 1. Now, find the derivative. F prime of x is equal to 3x squared minus 3 plus 0. And we're going to set that equal to the slope of the secant line through the endpoints. Now we solve for x to see what values of x would satisfy the conclusion of the mean value theorem. So I'm going to add 3 to both sides. I'm going to divide by 3. I'm going to take the square root of both sides. X is equal to plus or minus the square root of 4, which is 2, over the square root of 3. So we have, these are the two values of C that satisfy the conclusion of the mean value theorem for this function in A. What about B? B is f of x is equal to 1 over x on this interval from 1 to 3. Okay, I'm sorry, I put 2, 1 over x. Okay, so 1 over x is a rational function. But there is a theorem that says rational functions are continuous on their domain. As long as x is not equal to 0, it is on its domain, so we're fine. It's between 1 and 3. Also, it is a smooth curve, and it will satisfy, you can take the derivative, so it satisfies the conditions for the mean value theorem to be applied. So we want to find the slope of the secant line through the endpoints, so we evaluate the function f of 3 minus f of 1 over 3 minus 1. And so f of 3 is 1/3 minus f of 1 is 1 over 2. 1/3 minus 1 is negative 2/3 divided by 2 is negative 1/3. This is the slope of the secant line through the endpoints. Now, what's the derivative? Well, f of x is 1 over x or x to the negative 1. So the derivative is negative x to the negative 2 or negative 1 over x squared. Take the derivative, negative 1 over x squared, and set it equal to the slope of the secant line through the endpoints. And so we're going to solve for x, and that will tell us the places where the slope of the tangent line is equal to the slope of the secant line. So we will multiply both sides by negative 1. we can cross multiply here and get x squared times 1 is x squared. 1 times 3 is 3. X is plus or minus the square root of 3. Now I cannot remember where the video cut off before my phone messed up, so I might be repeating what I said before, but let me talk about the mean value theorem. This theorem is an example of what is called an existence theorem. Like the intermediate value theorem, the extreme value theorem, and Rolle's theorem, it guarantees that there exists a number within a certain property, but it doesn't tell us how to find the number. Now, the mean value theorem is important because it is a sort of a building block for which we use to prove other very important theorems in calculus. So that is 4.2.